In roughly 4 billion years, the Andromeda Galaxy, our most prominent neighboring cluster, will collide head-on with our cosmic home, the Milky Way. This collision, predicted from 12 years of Hubble data and research, will bring nearly 1 trillion stars from Andromeda together with 300 billion of the Milky Way, at speeds exceeding 300,000 meters per second. Pulled together by the mutual gravity of the black holes in the centers of both galaxies, and an unseen halo of dark energy surrounding the two. These clusters will collide, continue, and then unite, joining centers to form an energy mass brighter than the full moon, even from 10,000 light years away. Then, as the supermassive black hole at the center causes the stars closest to go unstable, the newly formed galaxy will explode outwards, scattering stars and solar systems into the darkest regions of our universe.
Matthew, get out of bed!
So sentimental, not sentimental, no romantic, not disgusting yet. Darling, I'm down and lonely. When we're the fortunate only, I've been looking for something else. These days it comes and goes. A list of many think less but see it grow. Like a ride, oh, not easily offended, not hard to let it go. From a mess to the masses, a list of many, think less but see it grow. Like a ride, oh, not easily offended, not hard to let it go. From a mess to the masses, follow misguided, stand still, discouraged.
Hi, we're here today at Smith Physics Institute to tell you about a collision that NASA's predicted between the Andromeda and the Milky Way galaxies in about 4 billion years.
No, we're not.
It's okay. I've got a Cassia.
Tell them what we're actually doing.
Imagine this, a collision between the polar star and an iceberg.
Here's what we're really doing.
In this collision, we've got a 400-gram bocce ball attached to some fishing line hung from the ceiling, and a 700-gram basketball mounted on a beautifully handcrafted cardboard sled.
The pendulum we've constructed shows our conservation of energy, while the collision shows the conservation of momentum, and the ball sliding to a stop shows work due to friction. Here's a brief video of our collision. First thing we're going to do when we look at this collision is analyze the energy transformation in the bocce ball, the pendulum swinging from potential energy at the top. As you can see here, we have the heights, the delta H, calculated the potential energy, converting this to the kinetic energy at the bottom. And we have this equation for the kinetic energy final of the ball. Ideally, we calculate with the mass we know and with the joules we calculated there, we get a velocity of 3.96. Ideally, we actually got 3.82, so we say energy is conserved. Kind of. We calculated the kinetic energy given our actual velocity, and we get 93% energy conserved. The next aspect of this collision that we're going to look at is the conservation of momentum. As you can see here, we have the formulas for conservation of momentum, and we also have the formulas that Smith gave us for calculating velocities of an object at rest and an object at speed once they've collided, what their final velocities are going to be. So we were able to calculate those using the ideal velocities for our initial ball speed, and we can say the momentum is conserved ideally because when you plug those into energy and momentum equations, they will add up. But here we have the real momentum conservation using our actual velocity of 3.82. So initial momentum, bocce ball moving that fast, you get 1.528. But final, we had the bocce ball bounces backward to negative 0.2 meters per second. The sled goes forward at 2.26, so we get 1.502, and using this equation, we get 98% of momentum is conserved. The last two aspects of this collision we're going to be looking at are coefficient of restitution as well as work. For the coefficient of restitution, we use this equation and use the actual velocities to get 0.62, showing this is a fairly elastic collision. And for work, we looked at work due to friction slowing the sled down, so we have the time it took the sled to slow down and the distance it covered. We calculate the acceleration, which we then plug into this equation to find the coefficient of kinetic friction. Once we have that, we can use our whole work, force, distance, and delta KE equations to get negative 2.56 newtons of force times the distance, and negative 1.79 joules of work was done due to friction because it stopped the sled.